Hi everyone and welcome back to this series about using the Python package Turbulucid for visualizing your unstructured 2D CFD data. This is the first video in the series, so make sure you've seen the first ones, part 0 and part 1, and this is part 2. So today we're going to primarily look at two things. That's extracting linear profiles and also vector plots. But before we go there, I want to talk about how to request help. And the best way to do that is to use GitHub issues. So if we go to GitHub, Turbulucid, we have this little thing called issues here. So if you click here, you can create a new issue. And here you can describe your problem. So this is better than sending me an email for several reasons. One reason is that I and everybody else gets to see that the code is used, so there's some commotion going on. That's one thing. Secondly, it's much easier to write code here if we want to, exchange some snippets or whatever. The third reason is that others see the answers I give to you, so maybe it also solves their problem. And there's also neat things like that if I, for instance, close a bug, I can reference the issue that you opened in the commit message and say that, yeah, this solves that issue, for example. So I very much encourage you to use the issues instead of contacting me privately. You can also do that, of course, if you really are against this method, but strongly encouraged. Second thing is the following. So I actually have a paper here, the link is right here, which describes the package. So you can read that if you want, but of course it is much less detailed than what I provide here in the YouTube videos. But if you use the package, I would be very thankful if you cite this paper in any written work, because citations matter in the academic world. In exchange, I'm going to add a little section here, which is going to be called works that use Turbulucid. And if you cite my paper and you want additional exposure, I will gladly put a reference to your paper under that section in the README. So it will be a mutually beneficial exchange. All right, with that out of the way, let's go into our Jupyter notebook. I have a bit of stuff here already, but not much. So first of all, I'm doing some imports, and then I'm opening a case. And finally, I am plotting the mean streamwise velocity, just the way we talked about in the last video. And this I do simply to expose the geometry of the case, which we're going to be looking at, and that's a periodic hill flow. We don't really care what flow to look at, but I guess it's nice to have an idea about what we're actually going to extract linear profiles from. So how do we extract a profile? So what I mean by that is that we want to look at how data is distributed along a particular line. Typically aligned with some coordinate axis, but not necessarily. So how do we do that? Well, there is a function called tbl.profile along line. So let's put a question mark and see the docstring to see what we're dealing with here. So as I said, as usual, the first parameter is the case. And then P1 and P2 are both two tuples. And they basically define 2 points, which define the line then. So the line is going to be crossing those 2 points. And then there's some additional parameters that we're going to talk about a bit later. But first, let's just do a simple extraction. So I passed the case. And then I choose, for example, x 0.1, y equal to 0. And then, well, let's take the same x for simplicity, and we can put an arbitrarily large y. It doesn't really matter. It's going to cut through the whole geometry anyway. So the important thing is that we have something above the top boundary. Let's see. Oop, we forgot to assign. So we should assign this to two variables. Now the first variable, y, is going to, or maybe y is a bad name, how to call it. Let's call it s. So s will contain the coordinates along the line where the data resides. Okay. And then the second one will be v, and that is actually going to be the values of all the fields that we have. Nice. So what we can do is write case fields just to see what is actually present in the case. We've covered that last time. And we see we got all of these fields here. Now, v is a dictionary that's going to contain the same entries as this. So we can do like this, right? Keys, let's see, do I need to print this? No, it's going to print anyway. So we can see that it's exactly the same things, right? So if we grab one of entries, for example, new t, it's a scalar. Yeah, then we get some data. Okay. So let's imagine I want to plot the values of this new t. Then what I can do is simply use pyplot. Nothing strange about this. And then s and v new t. Et voila. Naturally, the same thing if I want to, let's say, take the velocity, and then I should choose some component. For example, let's choose a vertical component. Excuse me. The vertical component, and we get some kind of random plot like this, because these are not averaged values. This will be smoother. But that's not to the point. So this is how you extract a profile along a line. Pretty simple. Let's discuss the rest of parameters that we have in this function. So let's again question mark to see the docstring. So the first thing is correct distance. Now this parameter controls what will be the, let's put it that way, what the first value in the S array will be. And there are two possibilities. Now let's imagine that I extract from -10 to 10 along the vertical direction. Now if we do that, and we look at S, let's look at the first 5 elements, let's say. We see that the first number is 10. Now, why is that? Well, that's because the first data point is at y equal to 0, but we placed our first point at -10. So that means if we start from -10 and we go upwards, we'll hit the first, the first data point at s equals to 10. Makes sense, right? But sometimes it's more convenient to just shift the coordinate system to wherever place the first data point appears, and that is what correct distance does. So if we look now, then the first value is 0. So this is the difference. Both false and true are convenient under different circumstances, but usually true, keeping it true is better, I would say. But it really depends. I mean, as soon as you figure out what this does, it's pretty easy to choose what you want. So that's one alternative we have here for our function. The other alternative is exclude boundary. Is a boundary of boundaries? Let's double check. I haven't forget myself. Let's check. Boundaries. Boundaries. And let's set that to true. And again, we'll look at this. And now we see that instead of 10, it's actually 10 plus a little bit. So the reason for that is that the data point we have on the edge at the boundary of a domain is now excluded. So this basically, yeah, I mean, this is all there is to it. Do you want to include the data you have on the boundary, or do you not want to include it? If you want to include it, then this should be set to false, as is by default. Otherwise, it should be put to true. Okay, so what else is there to discuss about extracting linear profiles? Well, one thing to keep in mind is that if the line that you create is not perfectly aligned with your grid, then it might very well be that you will get a bit of zigzags in the data. Actually, it's easiest to draw, I guess. So imagine you have, this is our geometry, and then we have some kind of grid like this, and the data is cell-centered, right? So this is like that. And then we're gonna define our line, and we're gonna define it, let's say something like this. Okay? So what this is gonna do is that it sees, okay, at this point, I'm crossing this cell. So I have to pick up the data, and what is going to pick up? Well, it's this. So this data point on your line is going to have whatever is stored in this cell center, which is may or may not be some distance away from where the line is located, right? So in this situation, you might get some kind of zigzagging in your data simply because of the fact that, well, you're grabbing actual data from a bit far away from the line. So that is normal. So there is no interpolation going on. That's what one should understand. You always get, if you cross a cell, you get its data points from the cell center. Excellent sketch. Let's not save this. Yeah, I think this is pretty much it. So we can move on to the vector plots. Let's remove this. Now vectors are plotted with the function tbl dot excuse me, plot vectors. Okay, so let's see what we have there. Case, as usual, then the field, similar to plot field, but in this case we should have a vector field, not a scalar field. And let's stop right. Well, actually we can say scale x and scale y are also familiar for us because we've seen that for plot field, so that's for scaling the x and y axis. And for the rest, let's not do anything right now. Let's just try to plot our first vector field first to see how it looks. So let's pass the case, and for example, the u mean. Small figure. Let's increase that. There we go. There are some artifacts, and the reason for that is that we are going, by default, we're plotting a vector at each cell center. And as you can imagine, if a grid is dense, that will mean that it will by default scale the vectors to be really small so that it can fit all of them in the figure. And yeah, if things become too dense, generally matplotlib starts artifacting a bit. Let's put it that way. So there are several things we can do with this. One is we can normalize the vectors so that all of them are of equal length. As of right now, it's actually scaling the length with the magnitude of the vectors that you provide. So if we want to normalize, we just write normalize true. Yeah, now it looks a little bit better, so the artifacts disappeared. So this is if you merely want to show the direction, right? So the issue here is that ideally, maybe we would like to have a bit larger vectors and also not at each cell center. So there's a way to do that. And the way this works is that instead of using each cell center, you define a rectangular Cartesian grid, which is going to sort of overlay your geometry. And you define the resolution of that Cartesian grid. And then a vector is going to be drawn at each point of that grid. So the way this is controlled is you set a sample by plane to true. So if you only provide sample by plane, it does create the Cartesian grid just as I said, and the resolution is set to some reasonable default value. Okay? You can control the resolution yourself though. And that is done by plane resolution. So let's say 25, 25. So this became a bit coarser. And I can make it even coarser. Yeah. One thing which is slightly weird is that the second parameter controls the resolution in X and the first one in Y. I should probably fix that. There's a historical reason for that because the VTK object, which performs the resampling, for some reason is constructed that way. But I think I might actually change that in a future release because even I myself get confused by this regularly. But in any case, this is how you control it. Let's go back to the docstring. So we covered this. Plot boundaries does exactly the same as what it did in the plot field function. That is, it controls whether you have this black border outlining the case geometry. So recall that one reason why you might not want to have it, so plot boundaries false, is that you can later choose to add that yourself. Right? But the difference is that now you have full control. So now you can say color red and the boundary is red. It's not possible to do that if you use the plot boundaries true in here instead. Nevertheless, it's set to true by default because typically one is okay with the black outline and you do need the outline. But keep in mind that you can have more customization if you do it separately. Okay, let's explore what we have left in the docstring. So we covered everything but this little color field parameter here. And if I read what that does, color field string or array, data used to color the vectors, either name of the field or an array. So basically this allows us to color the vectors with the values of some field. Now, unfortunately, currently that does not work if you use sample by plane. Okay, so we have to remove that. And then we can write color field. For example, new T. Okay. Yeah, so now you can see the vectors are actually colored by this little new T field which we have here. Can double check if we want. Yeah, looks legit. Okay, finally what is left is the quarks. And remember that the quarks are there to pass arguments to the matplotlib type which is being constructed inside the function, okay? And in this case, what is returned is a pyplot quiver. So plt quiver plots a 2D field of arrows, right? That's exactly what we're doing. So one can go for all of these different parameters one has here. For example, for customizing how the head and the shaft and blah, 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 blah over different sizes. But we're going to look at two things. One is scale, which is quite important. And that basically defines the size of the arrows. And the weird thing about this, well, at least to me, is that if scale is made larger, then the vectors become smaller. Okay, so let's plot this again. And then we're going to add scale, let's say 200. Yeah, as you can see, they become very small. If I instead do 20, they become larger. So typically it takes quite a bit of time and playing around with these quiver parameters in order to get a vector plot which looks actually nice. There's nothing I can do on my side to improve that. It's just that the quiver function is a little bit quirky and one has to, yeah, sit and tinker with the parameters. But in the end of the day, it's usually possible to get a pretty decent looking vector plot. The other parameter which is worth mentioning is colors. I think it's colors, not color. Or is it color? Interesting. It's color. Okay. It's a little bit confusing. In some of the constructors it's colors, and some it's color. So for quiver apparently it's color. And that just, well, as you can see, you choose the color for your vectors. Okay, so instead of, and this works perfectly fine with sample by plane, unlike the color field, where you grab colors from some data field. Okay, I think there is pretty much all there is to that. And in all honesty, this covers 90% of what I typically do with Turbulucid. So that's basically plot field, profile along line, and plot vectors. There are more stuff to talk about, so I'm going to continue the video series, but it's going to be a little bit more specialized. There is a function for streamlines, but it doesn't work super well because the associated matplotlib function is not so good, I think. There's also counterplots, which I guess in sometimes are very useful. We're going to talk about that as well in the next video, I guess. There's also quite a bit more one can do with the case. So we're going to look at that as well. I think those three things might be the plan for the next video. So stay tuned, and thanks for watching this one. I hope you enjoyed it. If you did, like the video. And if you have any questions, just leave some comments, either on LinkedIn or on YouTube. And yeah, hope to see you in the next episode of the series.